very excited to introduce today's keynote. Tom Goldstein is joining us from the University of Maryland, where Tom is the Volpe Kupel Associate Professor of Computer Science and also the Director of the Maryland Center for Machine Learning. Tom's research lies at the intersection of machine learning and optimization and targets applications in vision, signal processing, language, and many areas. Tom has been the recipient of several awards, including the Siam de Prima Prize, a DARPA Young Faculty Award, JP Morgan Faculty Award, Amazon Research Award, and a Sloan Fellowship. Tom is also the leader of a recent NSF program called TRAILS, which is a Trustworthy AI in Law and Society program. And so I'm very excited that Tom's going to join us today and tell us about some of his research. So please join me in welcoming Tom Goldstein.
Okay. Thank you very much for having me. I'm really excited to be here. It was really great seeing all the talks yesterday about really applied research problems. And some of the stuff I'm going to talk about today is a little bit more focused on future problems, possibly with generative models. But I'll talk about a whole bunch of different issues, and then you can see how realistic you think some of these are. All right. So here's an attack that many of you have probably seen. This is just a normal adversarial attack. So if you give this image to ResNet 50, it'll tell you that this is a cat. It's an Egyptian cat. It's 28% confident of that. There's only 28% confidence because ImageNet has a lot of different kind of cats, and the confidence is smeared out over all the different cats. But you can make a little bit of a perturbation to this. You just add a little bit of fuzz to the background, and now it's a 97% traffic light, right? So you've seen a lot of things. I think many people have seen a lot of these sort of demonstrations on blogs, but these are sort of parlor tricks. They're really focused on these academic toy systems. So one of the goals of my lab is to try to see if these kinds of attacks work on more sophisticated kinds of systems. Here's a project that we did a while ago. This is called the invisibility cloak. And we wanted to find out if we could make adversarial clothing that would make you invisible to an industrial strength object detector. So this is the YOLO2 detector, which was probably the most popular detector at the time, though there were other detectors as well. And I'm standing in front of a classroom at University of Maryland. You'll see that there's these blue boxes around all of the students sitting behind me, but there's no blue box around me because the YOLO detector can't see me, and that's because I am wearing this sweater. My sister says the reason this works is because the sweater is so ugly that the computer thinks no person would ever wear it. But actually, it works because there's a very elaborate optimization routine where we actually train this on a large data set with images of people to try to create a pattern that will suppress the entire feature map or in the area that the sweater appears. So we did this project, and I started selling these sweaters online to make money for my lab. I wasn't expecting many people to be interested, but surprisingly, the fashion media reviewed my clothing line. So the New Yorker wrote a piece about this. I was really excited to see what it said, but it said, the cloak looks like a baggy sweatshirt with garish colors and formless shapes. So it wasn't the best press. One of my friends was doing a fellowship in the UK at the time, and I got an email from her, and she said they had reviewed my clothing in the Times of London. I was excited about that. So she sent me a copy of the article because I don't have access to it. And it said, "This hideous jumper makes Professor Goldstein invisible." Also not very good press. But you know what? I was kind of happy about this because it acknowledges the technical contributions to my work. It says it makes me invisible. That's what I thought until I turned the page and it says it makes me invisible to the fashion curators at Vogue. So at this point, I realized this world of high fashion was not for me. I was actually doing a sabbatical in New York at the time, and I realized the fashion world of New York had chewed me up and spit me out. So I moved back to Washington, D.C., and I started to focus on other problems. But overall, the goal of my lab is really focused on this. How do we get adversarial attacks that work on toy systems in the lab? How do we get these kind of things to work on industrial systems in the wild? How can we sort of scale these things up? And lately, my focus is really on generative AI, because these are the kind of emergent systems that everyone is interested in these days. But also, it turns out there's all sorts of problems that potentially happen when you use generative AI. There's all sorts of interesting security leaks, data leaks, security problems that they can have that aren't actually so problematic for other kinds of systems. But generative AI is a bit unique And so I'm going to tell you about a few different kinds of problems that we see with generative systems. I'm going to talk a bit about passive data leaks. So sometimes the training data just leaks out of these systems without you even trying. I'll talk about active data leaks. I'll talk about adversarial attacks, and then I'll talk a bit about potential future mitigations for some of the social problems that generative AI causes by using watermarking. All right, so let's start by talking about passive data leaks. So to understand why generative AI is so problematic from a data security perspective, you just have to look at how it's trained. There's been a lot of work on trying to extract the training data or infer the training data set from image classifiers, but that's really hard to do because image classifiers, they throw away a lot of nuisance variables. A lot of the training data set information isn't really baked into the weights of the model. But generative AI is different. Generative systems are actually trained to reproduce their training data. If you look at the losses that they're trained on. So if you look at a diffusion model, the way that a diffusion model works is you take a big set of clean images, usually you take something like the Lion data set, which is 5 billion images scraped from the web. Some of those images are copyrighted, some of them are not, right? Some of them are creative assets that marketplaces use. Marketplaces sell those to graphic designers, right? And they appear all over the internet. But all of this stuff gets scraped. And then the way you train a diffusion model, you take a clean image, you add noise to it, you make it very noisy, and then you train a neural network to reproduce the original clean image, just a denoising system. That's all it is. You give it a noisy image, it spits back a less noisy image. But when you train on this objective, you're training your neural network to reproduce your training data. You give it something that is a very distorted representation of a training image, and then you're measuring its ability to reproduce at a pixel by pixel level exactly the data that it was trained on. So from a data set security perspective, there's something very bad, there's something fundamentally bad about the way we train generative AI systems. Okay, so how do diffusion models actually work? So I said you're just training denoising models, right? So you start by training the neural network to denoise a kind of noisy image. All right, if you give it a somewhat noisy image and you denoise it, you're going to get something that looks decent. It'll be a little bit blurred out because the model doesn't know exactly where all of the edges were supposed to be. It can't see all the fine details, but it will be a decent denoising. And so what you do is you start training on images like this, and you just crank up the level of noise higher and higher and higher until you're just basically giving it pure noise. You're just training the model to deal with these incredibly noisy images. And it will still do that. It'll denoise an image and it'll make it into it'll take a pure noise, it'll make it into something that seems like an image. But the images that you get back, they're not so good. They're really blurry looking. Now, the way that a diffusion model works is you just give pure noise to the denoiser, and you let it denoise it and try to convert it back to an image, but you're going to get something kind of blurry. And so what we actually do in practice is we do have these sampling processes where you take pure noise, you denoise it, and it gives you some sort of random image, but it's blurry, so we add some noise back, and then we deblur it with a lower level of noise, and you get something less blurry, and you just rinse and repeat, and you just do that over and over again. These are basically just denoising systems, and they're trained to reproduce their data. And so looking at these things, you might wonder how much training data do these leak? Do they leak copyrighted information? Do they leak people's creative assets from these graphic designer marketplaces? Do they leak people's personal photos? What kind of things do they leak? And we already know, this was pretty clear very quickly, that they can reproduce entire images in certain situations. But the kinds of images that they reproduce tend to be things that we're not so concerned about. They're things that appear all over the internet, usually because they're public domain. So you might say, give it a prompt. Give me the prompt here is just Van Gogh. This is Stable Diffusion 1.5, and you get some Van Gogh-y things, some of which are just perfect reproductions of Van Gogh's, but we're not super worried about that, and that's a known issue. But we're wondering what other sorts of copying are out there. Are there ways that these will copy information without doing whole image copies? Sometimes I'll ask it for a picture, and it's a little weird to me how crisp and specific objects are in those images. Some of these very specific representations of people, very specific representations of objects that seem very high quality, and I have to wonder if some of those are coming from training data set. And so what we did is we built a system that would search through an image database, and it would look for partial matches. So you'll give it an image, and it'll look through a database and tell you whether an image in the database shares something with that image. It turns out that's really different than the kinds of image search that we typically do. And so what we did is we built a training data set that we could train a system on to do this kind of search. So we took a bunch of images. These are images from the COCO data set, which is an object segmentation data set. And then we took objects out of this image, like this dog, and we just randomly placed them into other images with some sort of data augmentation. So randomized orientation and rescaling and color, right? So here they got this cat that's just randomly floating in the middle of space. But then we can train a system to look at two images. This is actually not such an easy problem, I don't think, to look at two images and tell you whether or not they share something. And so we built this system. It worked pretty well. We used it on a bunch of ImageNet diffusion models to look for this kind of object copying. And we didn't find anything, actually. We found that it wasn't really, the ImageNet diffusion models don't really steal anything from their training data set. And so we wrote a paper that said that for CVPR. And then we were running some more experiments on stable diffusion. And then the night before the publication deadline, because this is how things always happen, my student Gao to me sends me a Slack message because she found this image. And it turns out stable diffusion behaves really differently than other kinds of models. In fact, text conditional models have a very strong tendency to want to composite images by taking objects from a training data set and putting them together. This is an example of, this is a generated image. You asked it for a New Orleans house galaxy case. These are just image captions that are scraped from the web. And then you can see it generates this image, but then we find this image in the training data set. And what you find is that it basically just took this image from the training data set that was a different cell phone cover image, and it just replaced the cell phone with something different. And so this is actually an example of one of these creative assets. So this is a proprietary image that you can purchase on a marketplace that is used for graphic design purposes. But stable diffusion will basically regurgitate that creative asset for you and do the graphic design. So here's just another example. I like this one because it's sort of interpretable. So we gave the system the caption Hill Country Castle by Ardell Angel, and it produces this image, but then you look through the training data set and you find this image, and the caption for this image is Ben Hogan portrait, something, something, something. Right, so what's going on here? Well, if you look at this is the original painting, Hill Country Castle, by Ardell Angel. When you give a diffusion model this caption, it sees that it's supposed to be a painting by someone, right? It's a painting name and a byline. And so it thinks that it's supposed to be in a frame in an art museum. So what it does is it goes out and it finds a different picture of framed art, and it put a picture of a castle inside of it because it seems that sounds like it's what you want, right? But then it turned out that the background image is taken from the training data set. And here's the two images side by side. But I just think it's interesting because it's sort of interpretable what's going on. It actually just takes a wall photo of art and it puts a castle in there. You can kind of see inside the diffusion model's brain a little bit, right? Why it did that. In the case you think we're cherry picking too badly, we wanted to create situations by hand where this sort of behavior occurs. So we asked Stable Diffusion to generate an image of University of Maryland logo. This is a wall print of the University of Maryland logo. Here's a logo. And then you search back through the training data set and you find this image. Do you think this is a copy? What's copied? Seems like the sofa is very similar, right? There's a lot of gray sofas in the world, though I own a gray sofa. And you say that it's copied. Well, if we zoom in on this corner here, you can see that not only is it the same sofa, but it has the exact same throw on it with the exact same pattern of folds, right? The colors are a little bit different, right? But it's pretty clear that it's taken this sofa right out of the training data set, right? And one thing that's interesting about these systems, it's just an interesting thing that we discovered when we were doing this study, is that diffusion models seem to have some sort of reconstructive memory. I think that's interesting because humans also have reconstructive memory. We don't remember exactly what happened in a pixel by pixel way. We have some sort of semantic representation for something, and then we can reconstruct it approximately. And it seems that that's what diffusion models do as well. So here's an example of two images. This clearly one is supposed to be the reproduction of the other, but they're actually totally different. The ship is different, the waves are different, the sky is different, the mast is different, the sailors on the boat are different, the sails are different, right? It's a very different image. And yet it's still pretty clear that one is a reproduction of the other. Out of curiosity, let's do a show of hands. Who likes this image better? Do you like the left? Who likes the left better? Who likes the right image better? Your hand is up right now. You are a Philistine because the left image is a Rembrandt and the right image is cheap AI-generated junk. I also kind of prefer the right one, though. I don't know what that says about me. That's why I don't study art. All right, so there's a lot of legal implications for these kinds of copying behaviors. I mean, there's a ton of lawsuits going on right now that pertain to generative AI at large. Things that moved a little bit further with lawsuits related to stable diffusion in particular, just because these diffusion models, they came out pre-ChatGPT, right? So things are percolating through the courts a little bit more quickly than they are for language models. But these kind of copying behaviors, there are a number of lawsuits going on. And depending on how the courts choose to interpret existing copyright laws, we may end up with rulings that make it very difficult to build these kinds of generative AI systems in the future. I don't want to go too much into details of these different lawsuits, but there's people coming at this from a number of different sides saying these systems should be disallowed because they reproduce things like creative assets that are copyrighted and sold on the internet, or because in the case of Getty Images, because they don't like the way that these data sets are being curated and stored, and they think that it violates the Digital Millennium Copyright Act. But we will know, hopefully within the next 6 months, within the next year, what kind of regulatory framework we're living in with respect to generative AI. And right now, things are really up in the air. Okay, so that's passive data leaks. One of the interesting things, passive data leaks, these generative systems will oftentimes just leak training data without you doing anything. You don't have to try to make them leak training data, they'll just do it. But there are also active data leaks where you might try to deliberately scrape information from a system. One particular kind of system that's vulnerable to this is federated learning. Federated learning is widely used in a number of commercial products. Google famously uses it for their Gboard predictive text app. It's used for their Google's image recognition API. Apple uses it to do things like app monitoring, behavioral monitoring, to collect marketing data. There's a number of different uses for federated learning. One of the reasons it's used for these things is because it is reported to be private, because you don't actually send user data to a server for training, you just send gradient updates. So in federated learning, you have a model, that model lives in the cloud. You broadcast that model out to a bunch of small devices like cell phones. And each one of those cell phones has its own data. So you're typing on your cell phone and it has a small language model, a character-wise language model that makes predictions about what you're going to type. And it trains on your data. So it computes a gradient on some of those data samples, and then it aggregates them and it sends them back to the cloud. And so what the cloud receives is not the things that you're typing, it's just the gradient updates. And one of the reasons that federated learning is liked by these companies, I think there's a number of reasons why it is well liked, but one of the things that is widely marketed is that this is a privacy preserving mechanism. In fact, Google has an infographic that sort of seems like it's claiming that the level of privacy protection you get from federated learning is comparable to encryption. It prevents the server host from seeing your private data. Your private data only lives on your cell phone and nobody else has access to it. And so an interesting question is it possible to scrape data just by sniffing the updates of federated learning? If I have access to the federated learning updates that are getting sent back and forth to the server, is it possible to scrape people's private data from those updates? And there's a lot of work that's actually been done on this. Most of the attacks that people have demonstrated are approximate attacks that use things like gradient descent and optimization to try to find training samples that would generate the kind of gradients that you're seeing. And those work okay. They don't work very well against commercial scale systems. But this is a kind of attack that we presented. We first presented it 2 years ago. People now call this, we didn't call this at the time, but people call it the analytic attack. And one of the reasons why is because basically involves code analysis. I think I have it. I'll show that in a little bit. It basically, you can basically do detailed code analysis on certain kinds of systems, like you would in traditional system security, and find vulnerabilities and then exploit them. So anyway, here's how the analytic attack works. Here's the basic idea. Suppose that you have a neural network and the first layer of your network is linear. When you train this network, you'll take a training sample and you'll stuff it into this linear layer. So X is your training sample. It computes WX plus B. W is your weights, X is your bias. And that spits out Z, that's the output from layer one, right? Now you stuff Z into the downstream network and you compute some loss. So this is everything else that happens after that in your network, you compute a loss. When you train the network, you are going to compute the gradients of the downstream loss and you're going to broadcast those back to a server somewhere. So federated learning works. So I'm gonna make you remember your calculus. Don't know how that's going to go. You're going to have to remember your calculus. when you compute the gradient of with respect to W and with respect to B, you got to use a chain rule. So the way you compute the gradient with respect to W is you compute the gradient of the downstream loss with respect to Z. That's this grad Z term here. And then you got to chain rule it. So Z is equal to W times X. So when you're computing the gradient with respect to W, you got to multiply the downstream gradient by X. It's a chain rule. Now I want to compute the gradient with respect to B. That is the downstream gradient. And I don't have to multiply it by anything because B has an identity in front of it. Just multiply it by 1. So you look at this and you say, well, these are the two gradients that you get sent back for this layer. If you're a server, right? You compute these on your device and then you send them away. One of them is the downstream loss times your training data. And one of them is just the downstream loss. So what can you do to get back the training data? You can do, this is a very sophisticated attack. You do division. You divide one of these by the other, and you just get back a verbatim copy of your training data. And if the first layer of your network is linear, then these systems leak all sorts of information through the training gradients. So there's an example of federated learning experiment with a batch size of 16,000. So you're aggregating a gradient update from 16,000 users. And you can reconstruct verbatim copies of images from it if the first layer is linear, right? But the first layer of a network isn't always linear. There's more sophisticated attacks now that will exploit things like the linear last layer of your network and do a similar trick. But one was, you might think, when is my first, if I'm doing sophisticated machine learning stuff, when is my first layer going to be linear? Turns out there are situations where first layer is linear. One of those is when you're processing text. So we have this paper on what we call Decepticons, which is bad transformers that leak your personal information. We're all about terrible paper names, by the way. So this previous paper was called Robbing the Fed. These are my students. I don't take any credit for these horrible ideas. These are my students' ideas. All right. So anyway, why do people call this the analytic attack? Well, to make these attacks work on real systems, you need to do some code analysis. So this is the code that runs GPT-2. And if you look through this code, you'll find, you just basically go through this code line by line, and you can find things that are exploitable from a privacy perspective. In particular, there's this positional encoding that uses an additive positional encoding where you're adding positional information to the representations of tokens. And then there's a downstream attention layer. And I'm not going to go into the code of the downstream attention layer. I'm not going to go into any of this code in detail. I'm going to show you a pretty picture that tries to explain how this attack works. But to make these attacks work on real systems, you actually have to exploit a lot of different features of this code. And our paper on this actually goes through a bunch of different kinds of transformer architectures. And there's many different components of them that you need to piece together to really make these attacks work. But here's how a transformer works at a high level. I give you a sentence, the quick brown fox jumps over a lazy dog. You're going to take each of those words and you'll convert them into a vector representation. So every word in the language model's vocabulary gets converted into a vector, just a one-to-one mapping between words and vectors. And then these vectors are what go into the transformer. And the first thing you're going to do with those vectors is you're going to add to them a positional encoding. So there's a special vector that means position 1 and a special vector that means 2 and 3 and 4. And you're going to add those vectors to the embeddings for each of the words. And that allows the transformer to know that the word fox was in position 4 because the code for position 4 is added to this embedding. Then you're going to take that and you're going to, we call that a token. That's the input token for the model. And now we're going to stuff that into a fully connected layer. And we know fully connected layers leak all sorts of information. And then that goes into a downstream attention layer. And so what we're going to do is we're going to attack this fully connected layer. We can get a verbatim copy of the token that goes into it. And this token contains both the representation of a word and also the representation of the position that it was in inside the document. And then we can do an unmixing process that rips this token apart and figures out what the original word was and what the original positional embedding was. And if you, so this is kind of a high level view of this attack. There's actually, to make this work, for example, with large batch sizes or long documents, there's a lot of other properties of GPT-2 that you can exploit. You can't perfectly recover text all the time. So here's an examples with different text lengths and different batch sizes. This is, we did a simulated training on Wikipedia documents. And this is a slice of a document on ancient Egypt. The words highlighted in blue are when we get a perfect reconstruction of the word and its position. And when it's not highlighted in blue, we don't know the exact word and position, but we can try to infer it from the information that we have. And for a lot of these situations, we can get back, almost every word and position combo. So you can get a pretty accurate reconstruction just by looking at the federated learning update that gets sent back to the server. All right, so there's an example of an active data leak. Then there's also adversarial attacks. Adversarial attacks on generative systems exploit things like optimizers, right? They're not like the analytic attack that exploits the mistakes in your code. They actually exploit gradient descent and all sorts of mathematical tricks. There's an example of an adversarial attack on a commercial system. So there's a photographer named Steve McCurry. I actually follow him on Instagram. He's amazing. But he has a lot of famous photos. His most famous photo is this photo, Afghan girl. It was on the cover of National Geographic at one point in the 90s. So it turned out mid-journey, anytime the word Afghan showed up in your prompt, it would reproduce this photo, and his company wasn't happy about that, and they sent a cease and desist letter to Midjourney, and they said you can no longer reproduce this photo. And Midjourney said, okay, we're going to try to block that behavior somehow. So what they did is they just blocked the word Afghan. So if you put the word Afghan in, it will just tell you that there's something wrong with your prompt, and you can't use that prompt. So how good are these kinds of control measures? So we wanted to be able to do adversarial attacks on the language pipeline of generative systems, but doing that is kind of tough because when you're optimizing text, text is discrete, right? Text is not like an image where the pixels have continuous values. I know how to use gradient descent to update the value of pixels. I don't know how to do gradient descent on words, right? If you compute a gradient, you have the word the, you can't add a continuous valued thing to that, right? And so we created what we call a text optimizer. It's an optimizer that basically can do gradient descent on text, and you can use that to do all sorts of weird things with language plus vision models. So here's an example of an image, and I want to create a prompt that will force Stable Diffusion to reproduce something similar to this image. So what we do is we actually cook up a loss function that measures how well the output of Stable Diffusion matches this input image. And then we do gradient descent on the input text to try to find a sentence that will give you a good match. And then the optimizer finds this. It says teddy bear emoji, cuddly teddy skateboarding, comforting NYC LED CL. So according to the optimizer, that is the best possible prompt that you could use. So how does a text optimizer like this work? And there are now some other more sophisticated text optimizers, but I think this is the kind of basic outline of a simple one. So words, they live in an embedding space. Remember I said that every word in your vocabulary gets converted into an embedding vector. Those vectors, they live in a continuous space, which is vectors of numbers. And I can do gradient descent on embedding vectors. I just can't do it on words. So what I do is I come up with this quantization operator Q that will take a vector that lives somewhere in embedding space. It doesn't have to correspond to an actual word, just somewhere in embedding space. And it will snap it onto its nearest neighbor word. And once I have that quantization operator, I can use that inside of a gradient descent routine. So I might have I want to minimize some function. That function might be, for example, the clip score similarity between an output image and a starting image. And I want to do gradient descent on that. I want to find the text input that minimizes that loss. And the way I'll do it is I'll just start with an embedding vector representation for my text. I'm going to just look at the embedding vectors, not the words themselves, because I can do gradient descent on those. And I'll compute the gradient of my model, and I'll do gradient descent on these embedding vectors. But before I compute the gradient, I'll just run this quantization operator, and I'll snap everything onto its nearest neighbor word. And it turns out that that actually works pretty well. It allows you to do gradient descent on text. So here's some examples. Here's the original images that we're going to input. That we're going to input into our system. I'm going to run a text optimizer, and I'm going to try to find a description of these images that will cause Stable Diffusion to reproduce a similar image. You don't get back the exact same image because Stable Diffusion is random. If you give it any particular caption, it will generate different variations on the image every time, right? So we're not looking for pixel by pixel match. We're just looking for something that's semantically the same. So you run the text optimizer. The text optimizer is very clever, does a much better job than a human can. Right, it's hard. Human creativity is generally not a match for the cold, calculated power of a machine, and this is definitely one of those cases. So you put in this first image and says, "Thankfully, Aviator Doge," like the optimizer knows to evoke a Shiba Inu, you use the word Doge, right? And this all just comes out of a discrete optimization routine, right? There's nothing handcrafted inside of this. Appreciates, manage fundraising pricing. You give it this image, you get like a kind of similarly, in some ways, cryptic caption, but it does a really good job reproducing the image. And sometimes it'll even work. You'll ask for a 3-word description. It'll give you a very concise 3-word description of an image that does a pretty good job reproducing it. Okay, so one of the reasons we developed this optimizer was originally we were interested in adversarial attacks. And if you have a text optimizer, you can do adversarial attacks on text systems. But the first version of this paper that we wrote was basically just about how you automatically extract a description of an image that can be used inside of Stability or Midjourney. And it turned out this got kind of popular online. People really like this because you can take an image that you like, you extract a description of it, and then you can edit those descriptions by hand. There are other methods like textual inversion you may have heard of that will come up with some sort of continuous vector representation of your image that you can use, but that's not interpretable and people can't edit that. So there's a subreddit of people that like to use PEZ to do things. And we're gearing up to write a paper on adversarial attacks. And then somebody on that subreddit kind of came up with adversarial attacks themselves before we got to it. And so this is basically talking about this experience this person had with PEZ, where PEZ is our text optimizer, where they said that they took this album that has a bunch of digital images that look like this. And then they asked PEZ to make a bunch of prompts, like, if you give it enough tokens, it'll give you something like Lindsayana Shu Kasharma Premio something, fire. I don't know what the hell that's supposed to be. CG impressionist, blah, 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 blah. But just gave him a bunch of garbage. And he thought it wasn't working, but then he puts this garbage into Midjourney's API, and he gets back images that look like this. This is someone wearing, a very similar looking person with very similar looking hair who I think actually even seems to be wearing the same hoodie, right? Even though that these prompts to a human, they seem like garbage, right? So this person basically discovered adversarial attacks by accident. So we wanted to know whether these adversarial attacks would work in more realistic scenarios. And so remember this situation, right? Midjourney blocked this word Afghan. But it turns out that even with the word Afghan blocked, you can use a text optimizer and you can just compute a caption that is a feature collision with the word Afghan. I compute a sequence of words that outputs the exact same features that the word Afghan would, and then you can get back, very similar reproductions of Afghan girl. So here's an example. Here's the caption that you get. It uses the word Taliban to try to evoke the concept of Afghan, and so we ban that word too. And then the optimizer can still find a pretty good caption, but it uses the word refugee, so we ban that too. And then you get, I actually think this is the best reproduction of the image, but it gives you a pretty much uninterpretable caption, but you can still bypass these kinds of protections. There's a paper that came out more recently. This is from a team at CMU, where they show that you can use text optimizers to create attacks that would jailbreak ChatGPT. So let's say that ChatGPT is programmed not to do something, right? It's reinforcement learning has been used to cause it to refuse to do certain tasks. It's possible to come up with a seemingly uninterpretable adversarial prompt that will transfer to ChatGPT, and about 80% of the time these work. So you can jailbreak the model about 80% of the time. I think looking into the future, we also have some work on this kind of adversarial attack, just looking at defenses. But I think defenses for this kind of adversarial attack are important. If you want to be able to use, right now there aren't a lot of deployed use cases for these language models, but in the future, I think we'll probably see these kind of language models used for all sorts of things, particularly in customer service. Suppose that you are an airline and you have a chatbot that does customer service for you. Can somebody manipulate that chatbot into giving a refund when it's not supposed to give a refund? And they manipulate a chatbot into releasing PII when it's not supposed to release PII? Can you manipulate the chatbot into thinking that you've authenticated yourself when you haven't authenticated yourself? So these kinds of attacks, right now, I think they seem very toyish. Whether they remain toyish in the future is not so clear to me. I don't really know what the future is, but I think that this kind of automatically generated attack is quite interesting. And then finally, I'm going to talk about one last topic here. I'm going to talk about harm mitigation via watermarking. This is a little bit of a controversial topic. Some people think we should be doing watermarking. Some people think we should not be doing watermarking. But I'll tell you a little bit about watermarking, and then you guys can have your own opinions. Okay, so there's a number of security and social problems that are caused by language model abuse. And this particularly happens. And a lot of people in the news, you hear about people cheating on their high school assignments. That's not so motivating to me. What's more motivating to me is platform integrity and abuse of social media platforms. So for example, I had this tweet the other day. It talks about how you get training data sets for large language models. It says training an LLM takes about 1 trillion words, about 30,000 years of typing. It goes on and from there. And one of the top comments on this tweet was this comment. I'm amazed at the amount of data and time it takes to train an LLM. It's interesting to see the connection between this process and the Reddit protests. OpenAI's approach to training models in the entire internet is truly impressive. Seem weird to anybody? You spend a lot of time working with ChatGPT, which I do. It feels a lot like a ChatGPT-4 generated response. And also, his name is Derek Ponzi Trader. He has a handle that appears like it's probably procedurally generated. And then his profile photo is a picture of a man with physically impossible hands. And if that's not convincing to you, you can also go into this guy's profile and all the comments appear to be GPT-4 generated comments, right? This is not the only, what's interesting is, this particular thread that I wrote, it got a lot of engagement, and I find that you get a lot of bot responses. So we actually found there were about 20 comments to this, and 4 of them were written by ChatGPT. Right? So there's a lot of these bots out there on Twitter. If you think they're not there, they're there, and there's a lot of them. There's a lot of them. Sometimes they're obvious, sometimes they're not so obvious, but I think this is a rising problem. If you go on Amazon, you can find all sorts of reviews that look like this. Yes, as an AI language model, I can definitely write a positive product review about the active gear waste trimmer, right? As an AI language model, I don't have the specific cookbook in hand, but I can suggest some general guidelines. You see a lot of these kinds of things, right? And in the past, there's a lot of bot written, even before language models, there were a lot of bot generated. When you look at, you scroll way down in the reviews of an Amazon product, you'll see things that say, great product, very nice, right? A lot of these were bot generated, but in the past, Amazon has basically thrown those away and they get relegated to the bottom of the reviews and they don't really impact the product ranking. Now there's a lot of these auto-generated reviews. Most of them are not as obvious as these, right? But some of these attackers are not so sophisticated. But this is a big problem for Amazon, right? These kinds of reviews are just spamming their platform and it's not so clear what to do about it. People are also worried particularly about things going on Facebook. Can you create an army of bots that just respond to all sorts of posts with comments that promote conspiracy theories? Can you have an army of bots that you use to spread misinformation in some sort of election manipulation campaign? From a platform moderation perspective, it's very nice if platforms at least have access to tools that can tell them what is LLM and what is not LLM. That doesn't mean they have to ban all LLM content. It's just a very useful tool for them to have as part of their moderation toolbox. If you believe that this is hard, so one of the interesting things about watermarks, they particularly target low sophistication actors. Not everyone has to be a high sophistication actor to have a bot that spams things with Facebook. If you're not particularly technically inclined, you could just go on the Chrome Web App Store and get this app for your browser that just automatically spams your Facebook account with all sorts of ChatGPT garbage. Thank you very much, Google. Does this app work well? It probably does because the reviews are spectacular. So many 5-star reviews. Okay, so what can you do about this kind of behavior? One possible solution, there's a whole spectrum of possible solutions. One possible solution that's being discussed is that we could possibly implement watermarking in some of these systems. Watermarking, it basically puts an invisible signal inside of the output of a generative model that makes it clearly identifiable as generated by that model. So in this case, this is from our original watermark paper from January. This is before Llama came out, and so this is using the OPT model, which is not such a powerful model. But you ask it, we gave it a paragraph from our watermarking paper. We seek a watermark with the following properties, and then it gives us a list of properties. A minimal marginal probability for a detection attempt, good speech frequency, and energy rate reduction. It gives us this list, right? If we take just this generated text and we put it into an LLM, this is 23 words, we put it into a watermark detector, and it says that this is LLM generated, and its confidence is 99.999999999999994%. That's its confidence. Right. So the nice thing about watermarks is there's two things that are nice. One is that they're way more accurate than what I call post hoc detectors. So detectors that just try to look at LLM text after the fact without a watermark, but also they give you interpretable p-values to tell you how confident you are that something is actually generated by an LLM, and I'll explain how that works. So how does a language model work at a high level? A language model will generate a sentence word by word. So you give it something like, my chinchilla feels blank. And then the language model looks at that and it has to figure out what the next word is. So it goes into its vocabulary. Most language models have a vocabulary of about 50,000 words, right? So it's going to say sad, happy, livid, one of these things, right? And what the language model does is it generates a score for each of those words. We call that a logit. And that score just tells you how good the word is. And then it will sample from a probability distribution where it's more likely to take things with big logits. So in this case, it samples the word peckish. So how does a watermark work? And there's a number of different kind of watermarks now, but this is the simplest one. What we'll do before we generate that word is I'm going to take previous words in the sentence and I'm going to hash them and I'm going to use them to seed a random number generator. I'm going to use that random number generator. I'm going to color every word in the vocabulary either red or green with a random number generator. Now, if I'm coming back later, we're doing this at generation time. Later, I can come back and I can reproduce that coloring. If I see my chinchilla feels, and then I look at the next word in the sentence, I can reproduce the coloring for that word by hashing the previous words in the sentence and using the same random number generator. Okay, so I'm going to assign a random coloring to the vocabulary, and then I'm going to give a little bit of a boost, not a big boost, but just a little bit of a boost to the logits of words that are on the green list. That just makes them in certain kinds of situations when you have multiple words of comparable probability that you can choose between, it makes the model a little bit more likely to choose the green words. So then you sample from this modified distribution, and in this case, you choose the word livid. Okay, so because the coloring is random, a human will use red words just as much as they use green words. They don't get to see the coloring when a human is typing. But the language model does get to see that coloring, and it's slightly more likely to use green words than red words. Right, so this is an example. In this case, it's much better to have about a quarter of your vocabulary be green. So in this case, there's 26 words here, but there's actually 36 tokens. Some words are more than one token. A quarter of if a human wrote it, you would expect a quarter of the vocabulary to be green. And so a human should use 9 plus or minus 2.6 green words. But this text has 28 green words because it was produced by a language model. And I can actually compute the p-value of that. I can compute the probability that a human, by random chance, would use 28 green tokens. The human, in expected value, will use 9 plus or minus 2.6, right? So if you use this many green tokens, that's about a 7 sigma event. It's very unlikely to happen. And then I can actually compute the exact p-value for that event. And that tells you the confidence that you have this was written by a machine and not a person. So what kind of watermarks are we going to see deployed? Most of the big LLM companies have these sort of watermarks implemented, but whether they deploy them or not we'll have to see. Back in July, there was a summit at the White House, and a bunch of companies came away and said that they agreed with the White House that they're all going to implement watermarking. But what exactly they're going to implement it in and what that will look like is not so clear. I think the specific statement they made is they're going to watermark things that involve, I'm just trying to remember the exact word. It's like textual visual, right? It's like multimodal content, right? And so whether or not they committed to watermarking language models is not so clear. I think there is a consensus that they have committed to watermarking images. And so we're starting to see articles come out about what those image watermarks are going to look like. I'm not going to talk about how image watermarks work, but you can make spectacular image watermarks. But I thought the LLM stuff was maybe a little more pertinent to the afternoon sessions today, so I focused on that. But DeepMind just released an article about SynthID, which is their image watermark. OpenAI has announced that they're going to watermark DALL-E 3. And actually, Stable Diffusion is already watermarked. It was watermarked from day one, but not with a particularly sophisticated watermark. And so I think watermarks are going to play a role in content moderation in the future. But whether or not they will play a role for text is not so clear. I'm not sure whether there's an appetite to move forward on that at these companies, but I hope that there is. I personally hope that there is. Okay, so to wrap up, security for generative AI is really the Wild West. We don't really know what's going on. People have done work in this area. I've done work in this area, but there's still so many questions that we just don't know the answers to. We don't really understand the complete spectrum of data set risks and how to mitigate them. We don't have a good understanding of when things get memorized from the training data set and when they don't. We don't have good ways of controlling that. We don't have a good understanding of behavioral risks. So, for example, large language models, when are they jailbreakable? Can we be confident that we have secure ways of preventing them from being jailbreakable? And that's not just an issue. You see this example, where people say, okay, ChatGPT, how do you make a bomb? And sometimes it'll tell you, and it gives you some completely garbage description, right? Those aren't the real security issues with LLMs. What we're really more interested in is when they're used for customer service purposes by corporations, are they going to be reliable enough to be a trustworthy product? We also don't understand the legal risks. The courts right now are basically anticipated to completely rewrite the meaning of our copyright laws. And so you'll see right now, a lot of the language models that have come out, they have secret data sets. Llama 1 had there's a publication that tells you what's in the data set. Llama 2, it's a complete secret what's in the data set. I don't think that's because they're using any unusual data sources that are particularly untoward. It's just that as things move through the courts, it's become clear that even standard ideas we have about what kind of web data is allowable for training might be completely tossed up in the air in the near future. People just don't have any idea what's allowed and what is not allowed right now. But what we do know right now is that hiding the training data does not mean that models don't leak information. And I think in the past, we more or less assumed that models wouldn't leak information. Image classifiers, they just don't leak a ton of information, right? Image classifiers are just fundamentally more secure than generative systems. But with generative systems, you need to be very careful about how they're trained and very careful about how they're used if you're worried about information being leaked. This doesn't mean that security leaks are inevitable. It doesn't mean that there's no solution to these problems. There's already papers coming out that can solve some of these problems to varying degrees. But overall, a carefully designed system can avoid many known exploits. For example, a carefully designed federated learning system could be built in such a way that it's very difficult to extract information from it. And one other thing is that this generative AI is this a space where adversarial attacks and defenses might actually be realistic, right? These kind of attacks that I don't think have been realistic in the past, they might be realistic for generative AI. It might be that these kind of jailbreaking attacks are realistic in a commercial setting. It also is the case that adversarial attacks can defeat watermarks. In some situations, watermarks can be removed from an image by using adversarial perturbations. We don't know the degree to which that is true. In sort of academic context, that's already been demonstrated, but how well that will work against commercial products is not clear. But the effectiveness of the watermarking measures that we have and the other kinds of detection measures we have might actually come down to how sophisticated the adversarial attack pipelines are against these kinds of systems. All right, thank you very much. Here's some of the papers that I spoke about. I'm happy if you have any questions. I'm happy to hang around and answer them.
All right. Well, thank you very much, Tom. I'll get us kicked off here. I was wondering if you could tell us a little bit more about some of these copyright questions. And, you talked about kind of partial image retrieval and things like that. With your understanding of copyright law, can you tell us a little bit more about what the barrier or what the bar is of copyright violation in image and text, and would a partial stealing a part of a cat from a training data set constitute a copyright violation?
Yeah, so there's different attorneys will tell you different things, especially when they're working for one of these firms and they have a particular side that they're representing. I am not an attorney, but I can tell you a little bit about some of the issues. There is, there's this question of if a system is being used in a to create copyright violations in a substantial way, is it legal to host that system? And you might think, well, it's not Stability's fault that copyright violations are happening, right? But if you are knowingly participating in some sort of copyright violation enterprise, let's say that you're a company that prints, I don't know if people use Blu-rays anymore, but I guess some people do. Let's say you print Blu-rays, right? And someone comes to you and they ask you to make a large-scale copy run of some sort of media that they clearly don't have a copyright to. And you do that, if the government comes to you and says you did something illegal, you can't just put your hands up and say, I'm not the one selling it, I just make the copies. You can't do that. That's still conspiracy to commit a crime, right? But it's not necessarily conspiracy to commit a crime. So the key case in this space is called Universal versus Sony. So Sony started making these Betamax machines that had 2 slots, and so you could use them to copy a Betamax tape. And they got sued, and someone said this is used primarily for illegal purposes. People are making illegal copies of media. And the court decided that because these Betamax copiers have substantial non-infringing use, in other words, there's substantial enough legal use cases for them, Sony should be allowed to produce these machines. So the court had to weigh the severity of the legal use case of the illegal use against the merits of the legal use to make a decision on whether or not what they were doing is legal. I think most attorneys now think that most people, if you polled them, would probably say that like a product like Stable Diffusion has a substantial non-infringing use, but it's really not clear how that's going to be interpreted by the courts and how they're going to weigh those two things, especially when you consider the fact that I think most tech people are very friendly toward generative AI. I think I'm relatively friendly toward generative AI. When I ask people outside of tech what they think, people are much more hostile, right? Most of my friends that don't work in tech think that stability is, it's all copyright infringement and they're training on artists' images without compensating them, and it's all a huge problem. The judge that you get in the courtroom is not going to be a tech person. They're going to be somebody probably from outside the tech community. And those people tend to be much more hostile toward generative AI than I think people in this room would be. So it's really, like I said, it's the Wild West. We don't know what kind of decisions the courts are going to make. I think people are hoping that the court's decisions will overall be friendly to tech companies, but it only takes one of these, it only takes an adverse ruling in one of these cases to just throw a wrench in the entire system and completely we'll have to completely rewrite the way that we think about collecting training data and storing training data, using training data. Yeah.
All right. Any questions in the room, Byron?
I see a few of these questions echoed in our online Slack channel. So for those online, please do have them here. But Tom, with respect to watermarking, one of the, I think, anti-watermarking techniques is to, from a watermarked model, reproduce the text with a non-watermarked model so that the red green. And I think even in sort of digital watermarking, a similar thing now with generative AI can be applied. So the bits in the Lie-2 algebra of the watermark signal now are sort of regenerated, and that verification is destroyed. Are there efforts, or is there a state of sort of anti-tampering to address with respect to that watermarking attack?
So what I was saying about adversarial attacks is how secure watermarks are depends on how severe you can make these adversarial attacks. There's also defenses against adversarial attacks, right? So there's a cat and mouse game to be had here. I think one issue with watermarks is that I don't think they have to be adversarially secure to be useful. If you look, for example, there's a lot of low sophistication actors here that have access to apps like this, that produce reviews on Amazon that sound like this, right? There's a lot of low sophistication actors that I think would be caught even if these systems don't turn out to be adversarially robust. But the hope is that they will be adversarially robust. And right now, I don't think it's so clear how robust they are. My sense is that they're more robust than people think they are. There are situations where, so we have done a study, for example, on AI paraphrasing. You could take watermark text and then rephrase it with something like ChatGPT, which is not currently watermarked as far as we know. Those kind of systems are actually not very effective at removing watermarks. You would need because the reason why is because they tend to reproduce bigrams and phrases from the original text. And then so the watermark persists, you just need more tokens to detect it. So for example, if you have watermark text rewritten by ChatGPT, once you get about 500 tokens, so that's about half a page of text, it generally ends up being about a 5 or 6 sigma event. So you still get a pretty strong detection. But you could potentially build a more sophisticated tool. I don't think just asking their language model to paraphrase is a very good attack, but someone could build, put something on GitHub that has a very particular sampler inside of it that specifically avoids using repeated bigrams, and that would scrub the watermark. Now, how good the text is that would come out of that, I think sometimes it would be great, but sometimes it wouldn't be great. Sometimes there's going to be situations where it's not possible to reproduce the text effectively without reproducing the bigrams. But there's people trying to work on more sophisticated systems for that. What I'm trying to say is it's not clear how easy it is to remove these watermarks right now. Is it very easy? Is it very difficult? I think most people on the web assume that it's very easy, but I think most of the attacks that people have in their head wouldn't actually work very well against text. So it's not really known. There will be adversarial systems that can remove watermarks, but how effective, how reliable they are, right? Does it work 100% of the time? Does it work 90% of the time? Does it degrade the quality of your image? Does it not degrade it? How effective they will be is still not entirely clear. I think we're gonna have to find out.
Great. Any other questions? Constantine?
Yeah, I mean, this is not an area necessarily I'm familiar with, like, but didn't we go through with this with DRMs, right, for code, where people try to protect code and it will be broken and there's never really a solution. It just keeps going around and around.
Yeah. Sure, but I think though that's actually you can interpret that as an argument that watermarking is not effective. You can interpret it as an argument that watermarking is effective. If you look at something like the DMCA, I think few people would dispute that the DMCA was effective at preventing people from copying music, right, or copying video. And there's still open source tools that will remove copyright information from music for you. But it's just there's a higher bar you have to get over to access those, and that prevents a lot of people from doing it, right? I think that I think this harm mitigation is not the same thing as security, right? AI safety is not the same thing as AI security. I think it's okay to have measures that prevent some bad behavior, even if they can't prevent all the bad behavior from sophisticated actors that say run their own language model on Amazon and have some command line tool running from GitHub that scrubs a watermark. I think it's okay to just to have a system that prevents some of that bad behavior, even if you can't prevent all of it. But you can't prevent everything, right? There's always the case that someone uses an unwatermarked open source model, right? You can't stop that, right? So that's why I say that these are watermarking is a harm mitigation measure. It is not it's not meant to completely end these kind of LLM abuses. It's just a mitigation measure. That's all it can ever be. But I think that's okay.
So in like regular software development, there's like we can strive for this ideal of like perfect software. Like we could almost perfectly specify what we want for like human space flight, right? It's very well specified, and then you have extremely rigorous development. With machine learning models, like this foundational part doesn't exist, right? Because like the allure of machine learning is we don't have to perfectly specify. The machine's going to figure out probably what we want. So for in software, we kind of build up from a variety of bases that gets us to the point of security through obscurity is bad. With machine learning, have we kind of like violated or broken enough of these fundamentals that should we be rethinking that security through obscurity may be okay, or it may be the best we can do?
So I'm actually preparing a talk that I'm supposed to give next week, and I'm planning to title it "Security Through Obscurity is Still Security," mostly just to be a little controversial. But it's true, security through obscurity is still security. One of the problems with the adversarial community, this is something that drives me nuts, the adversarial ML community, is a lot of the values that we have come from the cryptography world, where we say a system is secure if an attacker with complete access to the system, including the weights of the neural network that you're using, cannot break it, then it's secure, right? But that's such an unreasonable definition of security, and it's also a completely unnecessary definition of security. If the attacker has access to the parameters of GPT-4, then it doesn't matter if GPT-4 is watermarked. They can just run GPT-4, right? Security by obscurity is used all the time for machine learning products. An example would be like Face ID on the iPhone. It uses a proprietary neural network, and there's actually an FPGA inside of your iPhone. And one of the reasons it's there is because if the parameters get leaked and it gets compromised, they can overwrite the model parameters in a fairly secure way that makes it very difficult. It's not the reason they implemented that in hardware and not software is they don't want people to extract those model parameters. So it's security through obscurity, right? Another example would be like YouTube's Content ID. They use a convnet to do a matching. When you upload a video to YouTube, it will run a convnet on the frames and extract features and then match that into a library to determine whether or not that content is copyrighted. an adversarial perturbation could presumably defeat that if you had white box access to the system, but it's protected by security through obscurity. I think that's a level, security through obscurity is a level of security that is acceptable, good enough for machine learning. And the reason I think that's okay is, like you said, in machine learning, where we don't have exact specifications, you can never have better than good enough, right? So trying to get beyond that to the level of, security we expect from cryptography, it's just not realistic, but it's also not hopeful to have that be the goal.
So like we're already there with like GPT-4 of like we don't have a great paper on what it is. So if companies are going to obscure what they're doing and how it does, it's just going to like the big companies are going to win. Like it's going to be very hard for small researchers to outcompete Google. Do you think there will be a point where it then hits tension with like government regulation of companies, like we've aggregated all of the AI into the large winners that tell us nothing, and now the government, there's going to have to be this like countervailing tension of they got too big and they won too much?
I mean, I don't know what's going to happen. My perception is this, you will have very strict regulations in Europe. They're drafting this AI Act, and how that's going to be enforced is not entirely clear, but there's clearly moving very quickly toward regulating AI in Europe. And China has extremely strict regulations. Language models there already have to be watermarked. They're all watermarked. But America is a different sort of place. We're much more hesitant, for better or for worse, to plow forward with regulations unless we can get all the interested parties on the same page. And I mean, look at what's happened with social media, right? People have been talking for years about regulating social media, but getting a big enough consensus to move forward has been very difficult. You do have people pushing for AI regulation. One of the reasons that there was a summit at the White House where everyone agreed to do watermarking is companies want to dodge regulation by finding things they can do that don't cost them very much. Watermarking is a thing they can do that doesn't cost them very much. And so it's good that they're implementing watermarking, but at the same time, you can see that there's this duck and weave happening where the companies are going to try very hard to avoid regulation. Will they be successful? I mean, all the social media companies have been broadly successful at that. Personally, I think we're unlikely to see any sort of strict regulatory regime for AI anytime in the near future in the US, but I could be wrong. What might save us to an extent, though, is that Europe is going to have very strict regulations, and it's going to be difficult for American companies to operate without at least adopting some of those regulatory measures. Yeah, so we'll see. We'll see what the future is. I'm not sure.
Thanks, Tom, for the amazing talk. I really like the part about adversarial attacks. And what is mind-blowing for me is, especially because adversarial attacks generated looks like garbage text, which is a bit different from classical adversarial attacks in case of object detection, in which basically the manipulated picture looks more or less the same. So let's say, what do you think about it? And let's say,
I was going to say, if you look at my adversarial sweater, some people would say that it looks like garbage, but getting all the way back in time is going to be
no, yeah.
Yeah, so I mean, not all adversarial attacks on images are meant to be invisible, right? This is an example where you give the attacker, the most effective attacks are by and large patch attacks, where you give the attacker an unlimited budget. They can do anything that they want. Anyway, sorry, I'll let you finish your question. I'm not trying to.
Yeah, no, I mean, the one presented when basically you can evade the diffusion model with some text that looks a bit strange.
Yeah, so the thing is that so right now, the way that you defend against these attacks is that the attacks we have today, so we have a paper that talks specifically about this issue. The attacks that we have for language models today, they produce this text that looks like garbage. They're very effective, but they produce text that looks like garbage. Shortly after these adversarial attacks were presented, they stopped working on ChatGPT. If you give it garbled text that just says, that text is confusing to me, I'm not sure how to interpret that, please try to rephrase your question in a different way. And so what they're effectively doing is it's some sort of perplexity filter. So if your text is high perplexity, if it seems garbled, then they're just not going to respond to it. And that perplexity filter is either implemented explicitly or through RLHF. They just RLHF the model not to respond to things that look garbled and confusing. But in the image community, these kinds of defenses are generally considered bad. If you have a defense that assumes a particular property of an adversarial perturbation, for example, that it looks like noise, image optimizers are so good that I can just add a term to my loss function that says, don't have the perturbation look like noise, make it smooth, right? And then the optimizer will just blast right through that, and you can make an adversarial attack that looks however you want, right? It's very difficult to defend against image perturbations in that way. I'll also mention that like GPT-4V, the vision API for GPT-4, has some sort of perplexity filter. They anticipated the adversarial attack problem. If you try to upload an adversarial attack image, not that we would try that, if you try to upload an adversarial attack image, it seems to get processed through a completely different pipeline, and the response time is way longer. So they also seem to be using some sort of perplexity filter type measure. For images, those kind of filters are not secure because optimizers blast through them. But for text, we don't know if those are secure. The traditional literature would say that they're not, but text optimization is a combinatorial optimization problem. Its complexity is much higher than the smooth optimization problems for images. And we don't have good enough optimizers to create adversarial examples that don't look garbled. You can try, but the optimizers that we have today just won't do it. They're not strong enough to optimize those loss functions. So whether or not I think that these adversarial attacks are a pretty powerful method for jailbreaking language models. Whether or not we can have language models that are secure to that is really going to depend on how good text optimizers get. And we don't know that right now. It might be that in 6 months, we have amazing text optimizers that can manipulate an LLM to do anything, and they can make those attacks look like anything they want, and they're impossible to detect. Or it could be that a perplexity filter works great. But this problem hasn't existed for long enough to know how hard it is to solve it. I think we'll probably know more in like 6 months to a year, whether or not you can break these defenses.
Thank you.
Hi, thanks for your talk. Sorry. A few years ago, I heard like capsule networks are able to, for example, like the attack you have here. Like I don't know if capsule network still works, but like it's harder to attack those capsule networks for these type of images. Can you design like neural networks that are similar, like ideal, like in concept that are that works for text for like stable diffusion, things like that?
So I think there at various points in time, there have been different architectures that people claim, for images at least, are more secure. But generally speaking, optimizers melt through all of them. So like there's certain kinds of batch norm that were thought to be secure, and then someone came up with an optimizer that just melted through it. Capsule nets have been thought to be more secure, but there's optimizers that can melt through that now too. I don't think architectural changes make systems fundamentally more secure, but they could benefit you because of security through obscurity, which is not our favorite kind of security, but it's still relevant. One of the reasons why these adversarial attacks work on ChatGPT, we don't have access to ChatGPT's parameters. So how do we craft the attack? You craft it by looking at open source models like Llama and its various fine tunings. You take all the open source models we have, we create an attack that works on those, and then it transfers to ChatGPT. Why does it transfer? Well, it transfers because all these language models use the same training data, right? Almost all the tokens are just common crawl. They're scraped from the same internet as everybody else, right? And they have very similar filtering strategies. So everyone's training the same model on the same data, and everyone's using the exact same network architecture. So changing the network architecture might actually potentially help from a security through obscurity standpoint, because it might be that these attacks wouldn't transfer if you just didn't know the architecture that OpenAI was using. We know almost exactly what their architecture is. That makes the attack really easy. It's not a huge appetite to try to solve the problem by changing the architecture, because the architectures we use for LLMs have been fine-tuned for years, and it costs so many millions of dollars. I mean, like training GPT-4 probably costs between $100 and $200 million. And trying a new architecture variant that may or may not produce good results. I don't think there's a big appetite for that, but that is one possible solution, but it's a pretty unappealing solution, I think, changing the architecture.
All right, we've got time for one more question we're going to take from online.
Tom, there's some discussion online, maybe a little fear about ongoing regulations and what that might mean in terms of impacting adversarial research, de-watermarking adversarial attacks. Do you have some comments on legal consequences on research?
That's also the Wild West. So for example, my lab right now, we're training a language model and we're talking to lawyers a lot about what kind of data sets we can use. It's very unclear. Even standard open source data sets, it's very unclear. So it's already impacting us. I think the biggest potential regulation that has actually been seriously discussed is the idea that you might need to have a license to create a language model or to host a language model. That would make it this is something like Sam Altman proposed this in his testimony in front of Congress. I've heard this idea batted around. I mean, if something like that were to be adopted, I think it'd be a disaster for academics, right? We don't have the financial resources to deal with licensing. So I think these things probably won't happen, especially in the US. I think that we probably won't end up with regulations like that, but it could happen. Yeah, a rule like that would be a complete disaster. I don't know how we could do open language model research anymore without open source model development. That could be a big risk.
All right, well, thank you so much, Tom. Everyone, please join me in thanking Tom Goldstein for this great talk.